Suppose we were to connect two 1.5 volt cells in series with each other, like this. What do you think the voltage read by the voltmeter would be? 1.5 volts, 3 volts, or 0 volts? What would make sense? Because that's the correct answer. What would make sense if we stack two batteries on top of each other in series? Aiden, what do you think? Yeah, 3 volts. We talked the other day about how all of the different size batteries are all 1.5 volts or multiples thereof because that's the chemical reaction. If I need 4.5 volts to run a device, but I only have room for AAA batteries, I can stack 3 of them in series and I can get a 4.5 volt battery out of that. It says explain your answer using principles of physics. I'm just going to say, I hope it's kind of intuitive. By the way, what if we flipped the top batteries so we had them facing each other? What would the net voltage be? 0. Okay. So why don't we just do this? Well, there's a bit of a problem here. So in many portable appliances, do you even know what CD players are anymore? Clearly, I need to change this, but CD players, when I first typed these out, were the thing. Flashlights, definitely, when you ever take the back off of a flashlight, put batteries in, you'll notice you're almost always stacking them in series. 2 or 4 or more batteries are used in series, as in the diagram above. In series, the effect is to increase the total voltage. Now, there's a bit of a problem. Because I total is V total over R total, if you bump up the voltage, what happens to your total current? Bigger, smaller, or stay the same? If V total gets bigger through the same light bulb, what happens to this answer? Brandon, bigger. You're going to drain the batteries faster, because remember, current is coulombs per second. In this system, this is great, but you're going to double the current. Both of these batteries will only last half as long as normal. So compare that with, so I wrote down here, the problem with doing this is now that each cell now has twice or 4 times, or however many stacks you're doing, as much current flowing through it as it would otherwise. If you stack 4 batteries on top of each other, the batteries are only going to last 1/4 as long as if they were on their own. What about connecting cells in parallel? If I put a voltmeter right there, how many volts do you think we're going to measure going through this resistor? I'll give you a hint, not 3. Jaya, what do you think? Let's ski. How many volts did I gain? Whee! How many volts must I lose? Or, I don't know why my highlighter was doing that weird thing, but it was kind of a cool effect. I could go this way. No matter what, each path is 1.5 volts high. So here, V total is 1.5 volts. But what this will do, if I put the batteries in parallel, each one is only having to contribute half the current. These batteries will last twice as long as if they were on their own. So our workaround, you may often see, especially for a remote, my calculator is a great example if you all look up. I'm willing to bet these first 2 batteries are in series, these bottom 2 batteries are in series with each other, but these 2 series and these 2 series are in parallel with each other to cancel out the fact that they're getting drained twice as fast. We then put 2 batteries in parallel with 2 other batteries, and that brings us back to now they'll last about the same amount of time as if they were on their own. So if you ever notice the batteries are going alternating directions, if there's 4 of them, I'm almost 99% certain that's what's going on in your remote device. There's 2 batteries that are wired in series. It's a 3-volt device. There's other 2 batteries that are wired in series. It's a 3-volt device. But then we wire those in parallel, and that way we're still getting 3 volts, but it's lasting twice as long, but also lasting half as long, so we're back to normal. Does that make sense for our chairlift analogy? Sure. Rechargeable batteries. become charged by connecting them to a cell that forces current back through the cell. So if I connect a 1.5 volt cell to a 6-volt charger, then first of all, what would be the direction of the current going through this ammeter? Would the current be pointing to the left, or would the current be pointing to the right? Which way is downhill? Find the highest chairlift on the mountain. Kyle, what's the highest voltage chairlift on the mountain's magnitude? 6. Downhill is this way. And so the current would be flowing through the ammeter to the left, or counterclockwise. The current is flowing this way. What we're doing is we're forcing current backwards through a battery. That's what you're doing if the battery is of the type that can recharge. That's how you're recharging it. Oh, and what would the net voltage be? Well, Kyle, you gain 6, but then you lose because you're going backwards through the chairlift 1.5. What would the net voltage be then? Yep. This voltmeter would measure a change in voltage of 4.5 volts. It says explain your answer using principles of physics. I'm kind of hoping it sort of makes sense with our ski hill chairlift analogy. If we turn the page. In terms of my ski hill analogy, cells in series like example 2, so like example 1, if this was 1.5 volts and this was 1.5 volts, that's like having two 1.5 volt chairlifts. You get off the chairlift Kenta halfway up the mountain, hop onto another chairlift, it takes you the rest of the way, but you're still getting a net voltage of 3 volts. You're still losing 3 volts going through the resistors. Cells in parallel, like example 2, are like two chairlifts which both lead to the same place. Some of you can use that chairlift. We'll use this chairlift. We'll all get to the same voltage potential as the other one. Opposite cells are like one up chairlift followed by a down chairlift. So this one here would be go up 6 volts and then ride the chairlift down to get further down the mountain. Key idea: positive means higher, negative means lower, even though electrons flow in the opposite direction. Current flows downhill from positive to negative. If you go from positive to negative, that means a voltage loss. If you go from negative to positive, that means a voltage uphill gain if you're going through a resistor. So, example 6. I stole this from a university textbook. This is far tougher than I'm going to ever ask you, but we can totally handle this. It says find the voltage difference between X and Y and find the unknown currents and voltages using Kirchhoff's laws. I wrote, note, a complete analysis of this two-cell in parallel is beyond the level of physics 12. I'm not going to ask you, well, we can handle it. Okay. Well, what was step 1? Hey, what was step 1? What was the first thing I always did? Label. Where is downhill? Find the highest point on the mountain. Where is the highest point on the mountain? Where is the highest chairlift battery? Yeah. Downhill definitely is this way, which means I can already circle that one for the direction. It's this way. Which way must the current be going over here? Well, if we're flowing in from the bottom and if we're flowing in from the left, Hannah, the current's got to flow out. Got to be that way. So that's downhill, downhill, downhill. All right. What was step 2? I want to try and find the total current leaving the battery. I don't see I total, but then I often will say, do I see amps anywhere? Joanna, do you see amps where? The 5. Oh, I know it splits up right here at location Y, but how many amps right here? How many amps going through the 3? I know 2 things. How many volts do I lose going through the 3? I'm asking, sure. I times R, so it's going to be 0.5 times, is it 1.5 volts, I think? Double check me. No, yes? Yeah. Okay. Now what? We're going to ski. Now there are at least three ski hills. There's this one. That doesn't help because I don't know the voltage here or here, and I don't know the current here, or I don't know two things. It doesn't help. There's no trick that I can do. I could ski this one. That creeps me out because I'm going uphill through a chairlift. I'll do that if I have to, but I think I'll try and avoid that as a last resort. You know what, though? I could also ski that one. Is that okay, Ashley? That one I kind of like because, Fahim, how many volts do I gain from this chairlift? Ski with me. Wee! I don't know how high. How many volts did I lose in this resistor? How many volts must I lose in this resistor then, if that's going to work for the 4? Has to be. It's got to be. How does that help? Remember the first ski run that I avoided? Now I like that one. Let's ski again. Fahim, how many volts did I gain from this big chairlift here? How many do I lose? Don't know. Oh, how many do I lose going through here? Whee! Did that get me to the bottom? How many volts must I have lost going through the 3.5 ohm resistor? How can I figure that out? 6 takeaway. Yeah, which is what? Which is what? Oh, beauty. So 3.5 volts. Knock, knock. I know two things. How many amps are going through that resistor? Oh, I can answer this question. How many amps is I right here in this top left corner? Fahim. How many amps in this top left corner? Okay, I filled in that blank. Good. Good. Kenta, how many amps right here? How many amps right here? How many amps going this way? How many amps right here? How many amps right here? How many amps right here? How many amps flowing out? Sorry? 1.5. I can fill that one in. Oh, how many amps are going through mystery resistor R on the right-hand side? Knock, knock. I know two things. How many ohms is mystery resistor R? 1.67? Is that right? Anything I'm missing? Let's see. I found both the currents where they wanted. I found the mystery R. I answered the direction. There! It actually turned out not to be too bad as long as I didn't panic. Relax. Kirchhoff's laws. That brings us to the end of our electricity circuitry unit. Except, got to practice. So what's your circuitry homework? I'm not wild about number 1. You can skip that. I like number 2, though. I like number 3. 4 is 4. Here we go. 4 is good. 5 is good. 6 is good. 7 is good. 8 is good. 9 is good. 10 is good. 11 is good. Mr. Dueck! There you go. So skip number one.